Yeah, so at least to keep the first one. And then can adjust the microphone here. Okay, hello everyone. It's 8:45. We will just start and hopefully we will end on time. So it's my pleasure to introduce the speakers, and this is the network and platform session. My name is Diego Gomez Sara. I'm a professor at Notre Dame. I will be the chair of this session. We are going to follow the same structure as other paper sessions. We will have the presenters. Each one of them will have 10 minutes. We will have a video presentation, which will be the third one, and then we will have Q&A by the end. So if you have any questions, please keep them by the end. There is a microphone there. And also, we will have questions from our online audience. So we will start first with the presentation, Reducing Access Disparities in Networks Using Edge Augmentation by Ashkan. Please, let's give him a applause.
Hello everyone, my name is Ashkan. I will be presenting our paper. Our work explores how the structure of the network can lead to unequal access to information, and our main focus is to address these inequalities and create a more fair and balanced environment. Here's the outline of the paper. So consider the importance of information access in, for example, scenarios like recruitment. LinkedIn is a good example that your network position can determine your access to important information like job opportunities. So if you have a better position in the network, you have an advantage when it comes to finding job opportunities. We use an independent cascade to model information flow in networks. So it's a standard probabilistic model, and we assume a uniform transmission probability of alpha. So each node spreads the information to its neighbors with the probability of alpha. In our instance, let's say node 8 is the source of information, and it spreads the information to node 1. Node 1 spreads it to 2, and 2 spreads the information to 4, but not to 3 and 7. So node 4 doesn't have any neighbors to spread the information to, so the transmission ends here. In the end, we have we have an access for each node, access probability that we represented as P of U and V, which represent the access of the node V to the information that node U has. So in our example, node 4 has alpha cube access to the information that node 8 has. Computing these probabilities is computationally challenging, so we use Monte Carlo simulation to estimate the accesses. So network formation often introduces biases in the structure of the network and creates disadvantages for individuals who lack access because of demographic and socioeconomic factors, and processes like a link recommendation can widen this gap in advantage between the nodes. So we consider the edges to be the biased input data in our setting, and we try to intervene to the network by adding edges to ensure an equitable access for all members of the network. So what distinguishes our work from other works in the area is that every node is a source of information. We assume that every node has a voice that should be heard, and we present the position advantage of a node as their access signature. We will introduce access signature as a vector of access probabilities to all members of the network. As you can see, there's a access signature for node 8, which is their view of the network. We use individual notion of fairness instead of deciding who deserves the information. We assume that everybody equally deserves to receive the information, which resembles the difference principle outlined by Rawls, which argues to maximize the benefit of the least advantaged node. So here we will introduce three measures of a structural advantage based on the access signature defined earlier: broadcast, influence, and control. Broadcast represent the access to the least accessible. So what is your access to everybody in the network? What is your minimum access to everybody in the network? And we quantify it as the minimum entry of the access signature. Influence doesn't care about everybody in the network. It just cares about the overall access of the node. What's your average access to the members of the network? We represent it as the average of the access signature. And then we have control, which captures how much control we have over the flow of the information. The formulation is complex, but resembles the betweenness centrality in information access setting. For example, if you consider a star network, the central node has complete control over the other nodes, because each pair of the nodes that try to communicate with the other, the information should pass through the central node. So we want to select one of these measures for our optimization problem. We argue that influence is not a good measure because it allows rich to get richer, and so the more advantage that you have, it's more probable that you gain more advantage if we want to optimize based on this measure. On the other hand, control only cares about the brokerage ability of the nodes. We don't want to optimize based on control because we want an environment, a social network that nobody has control over the information flow. In contrast, broadcast is a good measure because it promotes connections between minorities, and it reduces the influence and the control of the most advantaged nodes or central nodes. So our optimization problem is to maximize the minimum broadcast, or to maximize the minimum pairwise access between all nodes by adding a set of k new edges to the network. We introduced some heuristic strategies for our problem. One set of the strategies focus on connecting the most disadvantaged nodes, like BC Court. BC Court connects the nodes with minimum broadcast to each other. And another set focuses on connecting the most disadvantaged to most advantaged nodes based on the broadcast measure, like BC1, and based on influence measure, like influ. And we also have a random baseline for comparison, which connects nodes at random. So we conduct our experiments on real-world networks from 1,000 to 10,000 nodes. Our intervention budget is 200, and we use 4 network-specific transmission probabilities from slow spreading information to fast spreading. And we use 10,000 simulation to Monte Carlo simulation to estimate the access probabilities. So one of our main objectives is to increase the minimum advantage of the nodes. So we plot the performance of different heuristics in increasing the minimum broadcast and minimum influence among all nodes. We plotted the number of intervention on the x-axis and the minimum broadcast and influence on the y-axis. A better heuristic is the one that increases the minimum broadcast and influence the most. As you can see, influ and BC chord are the best performing heuristics here. So our second objective is reducing signature distances. So here we don't need to care about picking a measure. We only care about reducing the distance between access signatures. So we plotted the violin distribution of the signature distances among every pair of nodes. And on the y-axis is the signature distances, and we have actually three different heuristics and one initial access probabilities. Again, a more downward shift results in a better heuristic performance. As you can see, influ and BC chord are the best performing and greatly reduce the signature distances. And our last objective is to reduce the gap between the advantage of the nodes. So we compute the gap for 3 measures of advantage. And here we can see BC chord significantly outperforms influ, because as we discussed earlier, influ connects the minorities or most disadvantaged nodes to the advantage node, but BC chords promotes the connection between the minimum advantage node, and that's why the access gap is the reduction in access gap is more obvious here. So in summary, we in our problem setting, we say every node is a source of information. Access to all information is important, and we intervene to reduce inequality by adding new edges to the network. We introduce 3 measures of advantage: broadcast, influence, and control. And we say that one of our heuristic strategies that connects the most disadvantaged node together increases the minimum advantage, reduces signature distances, and reduce the advantage gap among nodes. Our work has some limitations, and presented here, and that's it. Thank you for your attention.
So questions will be for the end. We'll start the second presentation. David from Northeastern. Go ahead.
Hi, my name is David, and today I'll be presenting on behalf of my co-authors our paper titled Group Fairness Without Demographics Using Social Networks. So traditionally, group fairness definitions rely on group labels to define the groups of individuals we would like to balance outcomes amongst. However, in the real world, a lot of times these group labels, as you may know, are either unavailable due to privacy concerns, or maybe they're even harmful to collect. So this begs the question, how would we do group fairness if we don't have defined groups? In this paper, we ask more precisely, if we have access to a social network, is it possible to measure group fairness? With the added requirement that we would like to not introduce group labels at any point in this process. So accordingly, our paper offers 3 contributions. The first is that we introduce a novel measure of group fairness that does not depend on group labels and instead is based on homophily in social networks, which I'll get into in a second. Further, throughout the whole process, we avoid defining groups entirely. And instead, we predicate on pairwise similarities to define our measure. And last, we'll deploy this measure to 3 different tasks and show that across the board, we're able to actually reduce the inequality that is between groups. So let's dive into this further. Before going too far into our method, let's review homophily, which is this idea that there is a tendency for individuals to connect more with people they're similar to. So this is the common saying that birds of a feather flock together. And we've seen this across many different attributes and types of connections, such as some of the ones shown here. And this is well supported in the social sciences. But moving to our method, and I'll get into this notation in just a second, what we are considering is a world where we have these unobserved attributes, but they're guiding network formation. And then from the network, we can infer these pairwise similarities in terms of how similar people are based on their link connections. And so we can use these similarities to now reinterpret the outcomes. And what do I mean by that? Well, let's introduce a kernel K where entry ij is a similarity between individuals I and j. We also have an outcome vector y. And so this is, say, your score on a predicting algorithm. In order to reprocess these algorithms, we follow 2 steps. First, there's a similarity function, and then there's an economic inequality function. So let's look at a toy example where we have a simple kernel like the one shown here with very clear block structure. We also have an outcome vector y where darker values are better outcomes. If we apply this kernel into the similarity function, what we're doing is smoothing these outcomes, and we can see that the smooth values here reflect that the upper block has on average better outcomes than the lower block. We can now feed these smoothed outcomes into our economic inequality function, and that reduces to a much simpler operation. To make this a bit more formal, our full measure is this expression in red, where again there's 2 parts. The red function has the A function, which is the smoothing function, and then function F, which is the economic inequality measure. A common one is normalized variance, but there are other alternatives as well. Now, this begs the question how you would infer the kernel given a network in the first place. And our paper introduces one way to do this, but there are many that you could think of. So the method we take is we take the network and we embed it. Then given these embeddings, we can define a similarity matrix, say the cosine similarity between these latent embeddings. And then finally, our kernel could be the column normalized version of this similarity matrix. So on the right, you can see examples of this kernel applied to synthetic block models. As expected, these kernels reflect the block structure we expect in the planned synthetic block models. In terms of theoretical analysis, we position against the literature on economic inequality functions. And within this literature, there's this property known as additive decomposability, which is that the total inequality, f of x here, is exactly the sum of the amount of inequality that is within groups, and then the inequality that is between groups. So if we had, say, income inequality, we could look at the inequality within countries, and then add that with the inequality that is between countries to get the total inequality. Why this is relevant is that in the paper, we prove that given a kernel, we can reformulate this based on pairwise similarities and avoid groups altogether. So with pairwise similarities, we show that with additive decomposability, any function must also satisfy this expression here, where the right-hand side is our measure of group-free group fairness, and is also corresponding to the inequality that is between groups. And for full details, you can see the proof in the paper. So now let's move to some empirical results. We run experiments using our measure on real-world tasks. And across all of these, we use data sets that give us a network and also give us the sensitive attribute, which would normally be hidden, but we use these at evaluation time just to confirm we're actually reducing inequality between groups. Frequently, we use a baseline where we perform a naive approach of taking a network and performing community detection and defining groups in that manner. So the first task is node classification. We're looking at an example where we have a classifier labeling nodes 0 or 1. Let's say 1 is the desired outcome, shown in red. We can define a linear program where we restrict the minimum exposure or minimum value for these smooth scores. And what I want to draw your attention to is that as we increase this threshold, we can see that indeed the desired label is more evenly dispersed throughout the network. Our second example is directly based on the previous paper, where we're considering a situation of maximizing access to helpful information, say vaccine access information. And it's the same setup as before. We consider network information as cascading, but this information is given to initial nodes first. They then pass it to their neighbors. And the goal is to choose which information or which nodes to give this information to first. Our algorithm chooses these nodes by greedily maximizing the minimum smoothed value. And we compare this against baselines that maximize the total reach, the minimum individual exposure, and the minimum group exposure. In these plots on the bottom, our algorithm is in orange, and the y-axis is the ground truth inequality measured by the sensitive attribute. And we can see that for many of the graphs, in many seed budgets, our algorithm is able to achieve the lowest level of ground truth inequality in information access. Last, we apply this to recommender systems. So this is a setting where we have users and items. And for every user, we know their ratings on all of these items. And the goal is to rank all of the items for the user. And we need to balance objectives. On one hand, we want to rank items highly based on which ones the user likes. But then we also want to make sure there's group fairness among users. Namely, for a given item, we want to make sure it's recommended to all groups of users and not limited to just a few groups. We can perform a joint objective optimization, and across all of these algorithms, we get a trade-off curve. The main takeaway is that our approach in orange might be a little hard to see, is outperforming the baseline where you just consider all individuals independently. It is underperforming the ideal world where you have group labels, but that's expected in this situation. So to wrap things up, a few limitations to acknowledge. The first one is that we know that network datasets can be biased in how they are both collected and sampled. Further, our method requires discernible community structure in this network. Again, we're also assuming that the network is formed through a homophilous manner. And then we also acknowledge that this embedding process can require multiple rounds of tuning to construct this kernel. But nonetheless, a few takeaways to remember are that we present a measure of group fairness that is based purely on similarities and doesn't rely on hard groups. Further, we show that we can apply this to tasks and actually reduce the inequality among the hidden group labels. And again, at no point in the process do we infer the attribute or define groups in order to measure group fairness. Thank you. We'll take questions at the very end, but you can see the full paper here.
I got to start it and go to full screen.
Okay, just want to introduce.
Ready?
Okay.
That's it.
Perfect. And audio. Okay. No. So we will have our third presenter. She's Mihaela Kurmey, and right now she's she's not here, but she sent us the recording, and the presentation is called "Delayed and Direct Impacts of Link Recommendation." We'll start the video, and again, if you have any questions, we can keep them for the end.
Delayed and indirect impacts of link recommendation algorithms on social networks. This is joint work with Hans. In our work, we investigate the delayed and indirect impact of link recommendation algorithms on social networks. This is joint work with Han Zhang, Shangyan Lu, and Yixin Wang. Recommendation systems often focus on user content interactions. Studying the impact of this system has received a lot of recent research interest. However, a less explored area is social, user-to-user recommendations, where users and not content are suggested to each other as recommendations. Such social recommendations are ubiquitous on platforms like Twitter, Facebook, or LinkedIn. A significant part of the connections are algorithmically curated. Despite the ubiquity and relevance, studies that aim to understand the impacts of link recommendation algorithms face many challenges, since measuring causal effects requires comparing the counterfactual evolution of the network without and with recommendations. Without interventional access, the most prevalent approach is to use historical data and perform longitudinal studies. However, longitudinal studies lack natural growth counterfactuals, so the causal effect is typically measured with respect to pre-intervention networks. This estimation can potentially under or overestimate the true causal effect, depending on the temporal trends in the unobserved natural growth counterfactual. On the other hand, interventional access offers the opportunity to perform A/B studies, where some users receive and others do not receive recommendations. These studies are considered to be industry standard for measuring causal effects. However, they are not a panacea for lack of appropriate controls, because both the evolution of control and the treatment group are biased due to network interference. In our work, we're studying impacts of recommendation through simulation. We propose a dynamic social network that captures the feedback loop between natural evolution and algorithmic growth. Through the simulation, we find that link recommendations have surprising delayed and indirect effects. Finally, this allows us to articulate the evaluation biases of longitudinal and A/B studies. In our work, we propose an extension of the Jackson-Rogers network evolution model composed of two parts, the natural growth and algorithmic growth. In a natural growth, at each time step, a new node I arrives with a latent embedding sampled from a group conditional distribution. Upon arrival, the first phase of natural growth consists of meeting strangers. Here, the new node connects with strangers based on latent space affinity. The second phase of natural growth is meeting friends. In this phase, the new node connects to neighbors of neighbors with constant probability. Further, at each time step, in the algorithmic growth part of the network evolution, a subset of nodes receive suggestions according to a link recommendation algorithm. And a subset of these recommendations are added to the network. To illustrate the evaluation challenges, we focus on stylized settings and consider two types of link recommendation algorithms. First are neighborhood-based, where for a given active node in the network, the recommender selects among candidate nodes a distance 2 from the active node. Second, we consider affinity-based recommendations, where recommendations are selected with probability based on latent embedding similarity. Further, for evaluating the impact of these algorithmic interventions in networks, we consider several metrics, such as the Gini coefficient. This metric measures the inequality in the degree distribution of nodes. Another metric we consider is homophily, which captures the preference for within-group connections. Now we show some stylized findings. We first examine delayed impacts on inequality. Recall that high Gini coefficients mean high inequality. And we see that inequality slightly rises naturally in the natural growth process. When we add recommendations based on latent space similarity, we find that the recommendations exacerbate inequality over time, even as compared to natural growth. This disparity arises from nodes with high embedding norm having more visibility and being recommended more often. Friend-of-friend suggestions seem to boost inequality as well, as shown here by the rising blue line. Interestingly, when compared to natural growth, these suggestions actually decrease inequality, at least in the short term. Hence, we can see that without a baseline of natural growth, longitudinal studies could yield qualitatively wrong conclusions. Furthermore, we see that recommendations have surprising delayed effects after recommendations are stopped. Here, after time step 200, when recommendations stop, actually inequality spikes, particularly for the friend-of-friend recommender. The reason for this is that the network got denser when we added algorithmic connections. However, now newer nodes arriving later miss out on this benefit, so the once growing subset of rich nodes shrinks as the network increases in size, leading to increases in relative inequality as measured by the Gini coefficient. Now we will consider indirect impacts. We can split total effects into direct and indirect effects. Direct effects show how by adding algorithmic connections we impact the network, and indirect effects reveal how recommendations shape the future natural growth process. In our model, indirect effects come from mediated edges. Here's an example. Imagine a network at time t which has AB edge from a previous recommendation. At the current time step, a new node arrives, node E, and during the meeting strangers phase, E connects to A. If in the meeting friends phase, E connects to B, we call this edge a mediated edge because otherwise, without the presence of the recommended edge AB, the node B would not be a feasible connection. So the edge EB is an indirect impact of recommendations. Such mediated edges are prevalent, and we see that their prevalence increases over time, and they are persistent even after recommendations stop. Besides being prevalent and persistent, they're also biased. We see that edges mediated by friend-of-friend recommendations tend to be biased in favor of bichromatic connections, while latent recommendations based on latent similarity tend to be biased towards monochromatic edges. So these have been just some small illustrative examples of various evaluation biases. We invite you to read our paper for a thorough discussion of other variants of network dynamics and a thorough discussion of the evaluation biases in AB studies. Finally, there are many exciting directions for future research, including theoretical formalizations, extensions to opinion dynamics, as well as developing methodology for debiasing evaluation in dynamic networks. Thank you.
Our fourth presentation, does AI-assisted fact-checking disproportionately benefit majority groups online, will be presented by Terrence Newman. Thank you.
Hey everyone, my name is Terry Newman, co-author of the paper, Does AI-Assisted Fact-Checking Disproportionately Benefit Majority Groups Online, with Nick Wilczynski, who's a fellow PhD student at the University of Texas. So first I want to discuss our motivation for studying this topic. So mis and disinformation continue to proliferate online. For instance, Facebook claims that it labeled 180 million posts as misinformation during the 2020 US presidential election. In response to the scale of this issue, some fact-checking organizations and platforms are using AI to assist in the fact-checking process. However, there's alarming trends related to mis and disinformation slipping through the cracks in minority communities, potentially indicating a systemic deviation in access to high-quality information based on one's position in the broader social network. So we aim to investigate whether AI may exacerbate this effect and to what extent it can be alleviated by algorithmic design choices. So as I mentioned, AI can be used to assist in the fact-checking process. In general, there are two main algorithms used. First, an algorithm is used to assess trending claims made on a social network, helping fact-checkers prioritize which claims should be fact-checked. Second, an algorithm is used to identify previously fact-checked misinformation that continues to be posted on the network, taking some sort of content moderation action like blocking the post or blocking users that post the misinformation. In our research, we're going to focus on design choices related to the first algorithm, which is usually called check-worthiness estimation. Typically, this algorithm is operationalized by predicting which claims on a social network may lead to the greatest harm for the general public if left unverified, using subjective judgments about claims as labels and text and network-based features to train the algorithm. In the next section, we're going to highlight our approach to studying the efficacy of AI-assisted fact-checking on mitigating misinformation consumption, which is a core contribution of our research. So there have been numerous publications in recent years that use probabilistic agent-based models to study misinformation sharing behavior online. These models are widely used for numerous reasons. So first, they tend to incorporate realistic agent behavior, such as limited memory, limited attention, limited access to information from across the network, which I summarize here as bounded rationality. Second, they can incorporate real social network structures from existing network data sets. Third, they contain model parameters that can be tuned, allowing for the calibration and validation of the model to real-world data. And fourth, they allow researchers to embed and test the efficacy of mitigations to the flow of misinformation. However, we noticed that in the existing literature on agent-based models of misinformation spread, little attention is paid to the role of online communities. In response to this gap, we developed the topic-aware community-impacted Twitter simulator, which we call TACIT for short. Our approach incorporates the 4 points we discussed on the previous page about agent-based models. Additionally, we assume that nodes within an online community in the network will have aligned interests, and that communities will be differently impacted by certain topics of information. Third, we assume that online communities have differing beliefs about certain topics, with some communities possessing ground truth knowledge and others believing misinformation to be true. Finally, we assume that there exists a small community of experts who consistently have high ground truth knowledge about an array of topics, such as journalists or scientists. Given these assumptions, TACIT simulates a microblogging platform similar to Twitter. TACIT takes as an input a community-segmented network. Communities can either be ground truth or detected from an algorithm using a measure like modularity. So when sharing information, nodes tend to tweet about topics that they are impacted by, and based on assumption 2 from the previous slide, nodes within a community are impacted by similar topics. Second, nodes read tweets from other nodes that they follow and potentially further propagate this information. Whether they propagate a tweet is probabilistic, and it's dependent upon their beliefs, their impactedness by the tweet, and the popularity of the node that shared the original tweet. Additionally, nodes have a set of information consumption behaviors that feed the dynamic nature of the simulation. Nodes read tweets from those that they follow. These tweets then update their beliefs. So if a node reads misinformation, they begin to believe more misinformation, and they'll begin to produce and propagate more misinformation. And on the other hand, if a node reads more anti-misinformation, they begin to believe more anti-misinformation, and they'll produce and propagate more anti-misinformation. If they read noise, this doesn't change their beliefs. This is kind of a null case of information in our simulation. Parameters in the tacit simulator are tuned to mimic real information cascade behavior, and we use data from the simulation as a test bed for evaluating mitigations meant to stop the spread of misinformation. Recall that we're investigating how design choices of check-worthiness algorithms impact the distribution of benefits from AI-assisted fact-checking. Using a framework for assessing diversity in socio-technical systems from Faisalpour and Diartiaga, we investigate 3 independent variables in the design process. First, who is represented in the training data? Second, whose views and knowledge are encoded in the algorithm? And third, who's included, benefited, or harmed by the use of the algorithm? Returning to our AI-assisted fact-checking workflow, we operationalize these variables in the following ways. First, we vary how claims are sampled from across the network to create a training data set. As a base case method, we look at the most viral claims across the network, which will likely overrepresent the majority community in the training data. As an alternative method, we sample the top N most viral claims in each community for our training data. Second, we vary who generates the labels used to train the algorithm. Motivated by recent works examining the wisdom of the crowd and identifying misinformation, as a base case, we take a random sample of labels for claims from across the network. We test 2 alternative approaches. One is a community stratified approach, in which there is equal representation amongst communities in data labeling. The second is a knowledgeable community approach, in which only the community with consistent ground truth knowledge about a topic is used for acquiring labels. Third, we vary how fact checkers use these predictions. As a base case, we assume that fact checkers simply use the predictions to rank order claims for fact checking, checking the top N-rated claims per time step. As an alternative approach, we assume that fact checkers stratify their workflow by topic. For instance, if there are 2 topics in the universe, fact checkers would check the top N/2 rated claims for topic 1 and the top N/2 rated claims for topic 2 per time step. Finally, we assume that algorithm 2, the algorithm that identifies previously fact-checked misinformation, is 100% accurate and always blocks known misinformation from being tweeted or retweeted. In order to assess the distribution of benefits from different algorithms, we measure the change in belief of each node throughout the course of a simulation. If we see a positive change in belief, this indicates that a node lost ground truth knowledge overall due to a high consumption of misinformation. A negative change in belief indicates that the node gained ground truth knowledge thanks to decreasing consumption of misinformation. Because we're in a simulation, we can observe every node in a state both with and without an AI-assisted fact-checking intervention. Therefore, we can precisely estimate the treatment effect of the fact-checking intervention on the node, which we can then average over all nodes within a community to get a community-level average treatment effect, which basically gives us the distribution of benefits from AI-assisted fact-checking. So we run these experiments with a majority-minority community that are impacted by different topics. We also include a small expert community that is very knowledgeable about the ground truth of all topics. We repeat this experiment on a Twitter followers network of approximately 13,000 nodes 10 times and report the results in the following section. So in this chart, we see the average treatment effect across communities in our experiment. The green bar represents the treatment effect of the minority community. The blue bar represents the treatment effect for the network as a whole, and the red bar represents the treatment effect for the majority community. First, we find that stratified sampling of training instances across communities provides significantly more benefit to the network than through a representative method for sampling training instances. However, almost all of this benefit is concentrated in the majority group, indicating that this method, while good for the overall network, could exacerbate inequalities in misinformation consumption across online communities. Second, we find that using labels exclusively from knowledgeable communities provides a significant benefit for both minority and majority communities compared to random sampling and community stratified sampling. While the majority community does benefit more than the minority community, both communities see a nearly 3 times improvement in average treatment effect when switching from random label sampling to knowledgeable community label sampling. This highlights the importance of using experts in the checkworthiness pipeline. Finally, we see that fact checkers can actively reduce disparities by stratifying their workflow across different topics. When they actively stratify their workflow by topic, they reduce the benefit to the majority group and increase the benefit of the minority group. However, it's worth noting that this means that the average node becomes worse off in the network, meaning careful consideration is necessary before implementing this intervention. So thanks for listening. Hope you enjoyed our talk. Feel free to reach out if you have any questions, and we have our code available at this link on our GitHub.
All right, our last presentation is here for Andres Dominguez Hernandez, and the name is Addressing Contingency and Algorithmic Misinformation Classification. The floor is yours.
Thank you. Hi, my name is Andres Dominguez Hernandez. This is the title of our paper, Addressing Contingency in Algorithmic Misinformation Classification. This is an interdisciplinary paper at the interface of science and technology studies and data science. And so we are also looking at automating fact-checking in this paper. And so I won't reintroduce it because the previous speaker did an excellent job at introducing this, but perhaps just to emphasize that these kind of techniques have been gaining prevalence in the last years. They have been taken up by major social media platforms, and they have been kind of using more automation and relying less on human moderation to tackle misinformation. And this led to more posts being taken down, but also to a surge in accepted appeals, which in other words means more false positives. And this is where we can start to see the ethical issues. So just briefly how, to say a bit about how these models work. They rely on the so-called ground truth datasets, which are collections of examples of truthful information and false information, which are drawn from large corpora of data, such as Wikipedia, or, as in the case that we're interested in here, fact-checker verdicts around the world. And so data scientists take these sources of truth at face value, that means as objective and reliable. And because of the potential of these tools to be deployed affecting billions of users around the world, there are important ethical, political, and epistemic implications which are rarely addressed in technical papers, and hence we wish to address here. So to critically assess these models, we go back to discussions in philosophy of science and in social studies of science about what constitutes a fact. And so this scholarship reminds us that there's a social dimension to facticity and truth. And so, in other words, facts are not just simply out there. And so scientific facts, for example, need to be observed, communicated, circulated in society. And so for that reason, what we consider to be the sources of truth is based on trust and legitimacy, which is gained through credential expertise, through credibility, reputation, etc. And so feminist scholars in particular have challenged the often loose language of neutrality and objectivity and in knowledge production because it hides the power dynamics that shape knowledge production. For example, Western male elite-dominated institutions of knowledge, research priorities, special interest groups, funding, etc. And so this is also true of fact-checker organizations who perform an important epistemic role in society, but can also be partial, they can also have political leanings, they can make mistakes as well, they are fallible. And so why is this important for machine learning moderation? So as these practices are being scaled up, this inherently social nature of truth becomes black boxed and hidden. And so, and most importantly, any accountability for errors and biases becomes replaced by a logic of model performance. And I will return to this point in a minute. So what we did, we used an interactive method we called coethnography, involving the co-authors of this paper, two social scientists, two data scientists. So the data scientists were actually building one of these models, and we wanted to interrogate it, scrutinize it. And we also looked at comparable works in the literature. I won't go too deep into this because of time, but we have a forthcoming publication on this, and you can also look at our paper. And so straight into the findings, we proposed this concept that we call algorithmic contingencies, which we define as key moments during machine learning model development, which could lead to different future outcomes, uncertainty, and harmful effects. So in the next slides, I'm going to be, basically what we did is we surfaced these moments, these contingencies, across the whole process of model development, from problem definition all the way through model deployment. And so I will pick up on some of the contingencies. I won't go through all of them because of time, but just to illustrate what we mean. So starting from problem definition, what we found here is that researchers use different theories and different definitions of the problem. So some might use misinformation, some use disinformation, some use fake news, and they also use different empirical studies to frame the problem. And so as this problem gets abstracted and translated into a mathematical formalism, these differences become flattened and hidden into the frame of misinformation classification. And so this leads us to the choice of inputs and outputs. And what's interesting here is that these choices of what goes into a model often depend on factors such as economic feasibility or opportunity. So for instance, what data is already available out there, easily accessible, etc. And this constrains the choices that we have and the tactics that we have to solve the problem. And so, for example, proxy variables might end up being used because of cost factors. And this can lead to spurious correlations between inputs and outputs. For example, very often humor is used as a signifier for misinformation. And the third one is ground truthing. We call it ground truthing when we start kind of training the models, and this is where most of the conditionalities are. Just to pick up on some of them. One of them, for instance, is that fact checkers might not agree on their verdicts over the same claim. So they might have completely different views, especially if they are talking about borderline cases. And because these models want to have discrete outputs, these nuances might get lost in the middle. And so there's also the fact that the ground truth data sets are highly temporally sensitive, so using historical data to assess new events over time becomes less effective. And finally, talking about some wider issues with model deployment, perhaps the most important one to highlight here is that these models are often positioned as solution to a very complex problem, following a utilitarian approach where some error or harm is acceptable. And so this framing shifts the responsibility to the producers and consumers of misinformation, thereby while underplaying the responsibilities of social media platforms in enabling the circulation of content that might be undesirable, including misinformation. And that means that the onus of algorithmic failures and harms falls on users. Okay, so what do we do about this? What's next after we highlight all these issues? First of all, we note that algorithmic contingency is not something that can be solved, but that needs to be made visible. So our recommendations are along the lines of improving transparency and accountability. So we have 3 tentative paths towards embedding responsible practices in algorithmic misinformation detection, which we argue are also relevant for algorithmic content moderation at large. The first one is about extending the practice of reflexivity beyond datasets. There's already a lot of important work around documenting datasets, talking about their provenance, their quality, their gaps. But we argue that we should go beyond that and look at the whole process of model construction, starting from problem statement all the way to deployment. The second recommendation is about conducting more situated and timely evaluations. In practice, this would entail, for instance, updating datasets in real time, even if that means reducing their size to reflect the availability of new information, but also using benchmarks of evaluation that are more sensitive to events, topics, cultural context, language, etc. And finally, we advocate for better accounting and reporting of uncertainty. Here, we include not only measures of quantitative uncertainty, for which there are lots of important work on that, but also qualitative measures of uncertainty, which should accompany any metrics of performance, and this should be used to provide a better understanding of a model's utility and potential limitations and failures. Thanks very much.
All right, we have just 5 minutes for Q&A. So if you have any questions, the microphone is there. In the time, just I want to, if you can come here, so we can be ready to answer any questions. All right.
So I have a question for the fourth speaker.
By the way, please introduce yourself.
Yeah, sorry.
Thank you.
My name is Andrew. I'm a PhD student at NYU in computer science. And so my question, so it's kind of 2 pieces, I guess. The first one is I noticed that you use agent-based models, and I've kind of been exploring something similar in my work. And one of the problems that I'm running into, and maybe you did as well, is sometimes it's hard to tell when you've incorporated enough behavior into these agents and simulated like enough behavior. If you go too far, or you think you're stopping too early, or like how you kind of make those decisions. And then the second piece, which is related, is do you ever try and validate, the way that you're modeling agents versus like real world data about social behavior? Just kind of curious about that.
Yeah, that's a great question. So I would say most of our assumptions about the model that we used come from previous works. The only kind of thing that we added or incorporated was that agents can have a different relationship to different topics based on what kind of community they're a part of. So yeah, we really kind of relied on the literature to guide that. And yeah, I didn't go over it in the presentation today, but we have a section in the paper where we do calibrate the model and tune it to real information cascades to show that, look, this is kind of at least similar to kind of information cascades from existing data sets.
Nice. Okay. Thank you.
Mm-hmm.
So I'm also very impressed by your work and kind of trying to find the common pattern here. So we have heard about optimizing, just adding edges in order to make more fair or more accessible information, also in order just like to spread information that comes from fact checkers. So I would like to ask you kind of like the pattern here, because of one thing, the trade-off is just the cost, right? Like adding an edge, basically it's just like it takes a cost. It includes like, for example, attention or just identifying or making a consensus. So I will ask you, feel free to answer this question, but like, what are the implications or the things that we need to consider in order like to implement the methods or the approaches that you're proposing here?
Yeah, I think, yeah, that's, I was thinking about that as well, because I guess the kind of recommendations that we put forward, it kind of asks that developers do more work, and that they kind of, especially if you want to maybe be more transparent, you have to do a lot more, and we ask a lot more than just documenting, but doing all this process of reflection. And so it's, it is kind of that compromise, and I guess, yeah, was kind of, perhaps I am looking at the process of before, like when these models are built, what we can do in each of these steps. And yeah, it's interesting to think about how that could be, because you, for example, are looking at what fact checkers or decision makers can do, and better to make better use of these systems. So it's yeah, interesting to think about how all these interventions can be combined. But it's true that it's always, it seems to be kind of a demand for more work and for more stuff to do.
I think in my case, the link recommendation algorithms already exist. So it's just a matter of replacing them with the new algorithms that we suggest. The only implication here, or the only thing that we should consider here, I think it's the feasibility of the recommendation.
Yeah, so I was examining these check-worthiness algorithms, which is kind of a first stage in the pipeline. So how do we surface new misinformation? And I think one kind of implication of this work is that it's really important to involve experts in this process to label the data. And you know, there's been certain changes to Twitter, such as like removing blue checks from certain people and maybe giving more people access to blue checks. They make it a little bit harder to understand who is an expert and who isn't. So yeah, I think understanding who is an expert and you know, kind of giving kind of a broad credence and not a biased credence to, you know, certain individuals is like, I think, a very important kind of step for that work.
I'll just say a few words. Yeah, building off of that, I feel like we all looked at information spreading, and based on my own experience, I think one challenge is there's a lot of choices in what metric you're using to measure how well the information is spread. And in the first presentation, we saw the Rawls individual fairness. You can also look at groups. But with networks, I think that there's a challenge of sometimes it's hard to tell if you're making a difference because some of these metrics can be non-robust. You can make maybe a small difference or a small change can lead to a large impact. So seeing if these changes are stable and robust to perturbations, I think, is a large challenge.
So it's time, and again, thank you for your presence, thank you for the speakers, and let's give them a final applause. Yeah. And if you have any final questions, you'll feel free to ask them directly. Hope to see you for the next sessions, and have a wonderful day, wonderful night.